Hi, this is Michael from Ansoft. In this video, we will compare the results from the limit equilibrium method with those from the finite element method. Results from ANSlope, example number 1, will be compared with those from EnFEM. Both ANSlope and EnFEM are products of Ansoft. In the ANSlope example 1 video, we demonstrated the steps to create a model in ANSlope. The safety factor using the simplified Bishop's method is 1.356. Now let's proceed with the slope stability analysis using EnFEM. Start EnFEM. Click on File, then select Import. A new import window will appear. Click on Import from ANSlope and open the ANSlope example 1.slpd file. The example 1 slope model will be shown in the main window. EnFEM will also import the soil properties from each layer. Default values of stiffness and Poisson's ratio are assigned to each soil layer based on the shear strength of the material. Users should revise these values based on laboratory or field test data. It should be noted that EnFEM treats soil layer with zero strength as concrete. We should change the stiffness to a very small value to simulate tension zone with zero strength. Select material properties from the data menu. Choose material number 2 and click on Edit. Change Young's modulus to 1 PSF. Save and exit. Select Auto Mesh Generation from the Pre-Mesh menu. A coarse mesh of the model will appear, and the program will switch from the design mode to the mesh mode. Now we are ready to run the analyses. Select Run Analysis from the Analysis menu. Select both the initial soil stress and the stability SRM stages. SRM stands for Strength Reduction Method. Click Run. A window terminal screen will appear, displaying the progress of the analyses. Once complete, a log file summarizing the analyses will appear. Users can select the result mode to view the result. Click on Plot Contour to see the deformation. By default, the contour plot shows deformations in the horizontal direction, U1. Change variables from U1 to U magnitude. A clearly defined sliding block can be seen in the figure. The failure surface is close to a circular surface. Users can select Show Contour on the deformed body and increase the scale factor to see the deformation at each loading increment. The safety factor is 1.501. Users can refine the element size in design mode by selecting Global Seed in the Pre-Mesh menu. Change the global mesh size to 3. Click on Assign and close the window. Regenerate the mesh using the Run Mesh Generation in the Pre-Mesh menu. Run Analysis from the Analysis menu. The resulting safety factor is 1.461, which is higher than 1.356 from the simplified Bishop's method. The higher safety factor is likely the contribution of the lower, stiffer layer and the assumption of an elastic material for the topsoil. To save analysis time, we can increase the size of elements outside the region of interest. Select Local Seed Control in the Pre-Mesh menu. Hold the Shift key and select the edges outside the region of interest. Right-click to end selections. Enter 6 for uniform size. Regenerate the mesh using the Run Mesh Generation in the Pre-Mesh menu. Back to the initial example with the tension zone. Instead of assuming zero shear strength, the tension zone can also be modeled as surcharges. It should be noted that, in limited equilibrium analyses, the zero shear strength approach assumes that the tension crack occurs along the circular failure surface. By modeling the tension zone with surcharges, the tension cracks are assumed to be vertical, and the factor of safety will increase from 1.356 to 1.483. This is because less soil mass is included in the sliding mass. Import the ANSlope file with surcharge into EnFEM and run the analyses. The resulting safety factor is 1.539. Similarly, users can refine the mesh by changing the global mesh size to 3. The resulting safety factor is 1.493, which is slightly higher than 1.483 from the simplified Bishop's method. Users can overlap the results from ANSlope and EnFEM in a graphical program like PowerPoint to compare the critical slip surfaces. In summary, compared to the limit equilibrium method, the finite element method requires more input parameters, such as material stiffness and Poisson's ratio. Additionally, the finite element method cannot provide solutions for materials with zero shear strength. The safety factors calculated using the finite element method are similar to those obtained from the limit equilibrium method. Thank you. For more information, please visit ensoftinc.com.